All right, so our last lesson is going back to approximating, which seems a little weird. Like, okay, if we just figured out how to do these things and evaluate, why are we going back to approximating? But just think of this as an easy lesson in that you kind of have the idea um, and we're finishing up with it. So it's the idea similar to Riemann sums. Remember, you see Riemann and you think rectangles. If, however, you see the word trapezoidal, use a trapezoidal sum, well, then you can pretty much guess, well, I betcha I'm going to use trapezoids instead of rectangles, and that's exactly what you're going to do. So let's think back to, you know, when we did Riemann sums. The first thing we figured out was the width. Now let's draw a picture. If I'm drawing 1 over x squared in quadrant 1, if I'm going from 1 to 4, I don't need anything outside of quadrant 1. That is, wow, that is just an ugly graph. Sorry, my perfectionism can't handle that. So it looks something like that. So I'm going from 1 to 4. And just like a Riemann sum, if you draw, you probably won't miss it. Remember the first thing we figured out when we were doing a Riemann sum, we figured out the width. And what was our formula for that? Well, it was the how much space you had to cover, so subtract the bounds, divided by the number of trapezoids or rectangles that we use. So in this case, the number of trapezoids. So I would get a width of 1. So that's kind of nice. I'll try to make it equally spaced. So 1, 2, 3. Oh, that's pretty good. And so you can see your trapezoids taking shape. Here they are. You have 1, 2, 3 trapezoids. So how you draw them is both of these sides are on f of x. So that's going to go there. This is going to go all the way here. And then you're going to make a trapezoid out of that. And those are going to be your trapezoids. And you're going to find the area, of course, of each of these trapezoids. And that's going to be approximation for the area under the curve. Now remember the trapezoid formula, as we've done this, because we've been finding these areas when we're looking at other curves. It's the average of the bases, or base 1 plus base 2 times the height. So notice when what we called the width, if I look at the trapezoid, my bases are these right here, base 1 and base 2. The height is this piece. So what was the width of the Riemann sum becomes the height of the trapezoid. So that's what you actually found. And just like we did before, I think you would agree that we kind of like to simplify the writing. And since we've done rectangles, wouldn't it be true that this height in all of the 3 trapezoids I'm finding would be common? So most people like to take out a common height. So let's do our integral. And again, we are estimating, I'm going to write it down here so I have a lot of room here. This integral is going to be approximately the height I'm going to pull out. And won't they all have 1/2 in them as well? So I'm going to pull out not only the 1/2, I'm going to pull out the 1. Now, obviously, you do not have to write the 1, okay? But just showing you that this is the common height. And then what would I be doing? Well, what's left for each trapezoid is base 1 plus base 2. So if I look at trapezoid number 1, my base 1, remember my function is 1 over x squared. So if I want to get the y value, I'm going to plug into that. Wouldn't that value of base 1 be 1? And the value of base 2 would be 1/4. That would be trapezoid 1 plus trapezoid 2. You have this base again plus you would have this base of 1/9. And then finally, you would have 1/9 plus and then 1/16. So that's going to be my what I need to type in the calculator. Again, if you had to get a value, you could type that in, and I'll give you a second to do that. So I might as well, come on calculator. So I have 0.5, that's the 1/2. I won't type in the times 1, times 1 plus, now I could do 1/4. I know that decimal, that's probably a little faster. So 1 plus 1/4 plus 1/4 plus 1/9. I'll do that one as a fraction. Plus another one of those. Again, this is to, if you had a multiple choice and you had to get they had a calculator portion and they had the decimal answer. So I have 1/2 times all that stuff, and I hit enter. And so this decimal would be, by the trapezoidal sum, would be approximately 0.892. Now, if you look at this one, especially if you have a lot more trapezoids, some people would say, couldn't I make that typing in a little easier? Because if I look back at my picture, move this guy out of the way, so I left a little space in between there. If you notice, if I have a common height, this is only if a common height. Some people, especially when there's a lot more trapezoids, do you notice that I use the first base one time and I use the last one time, but all these that are in the middle, because they're the edges of two trapezoids, I would use twice. So sometimes people say, okay, I'm going to do 1/2 times the 1. I'm going to do my first and last once, and then I'm going to do 2 times all the rest. If you like that, that's fine. If you don't like that, don't do it. But I just want you to be aware, a lot of times I do use that first and last once and all the middle ones twice. So if you see that on my keys, I want you to be aware of, okay, what is she doing? So that's what I'm doing. But again, you can only do that if there is a common height, because if there's not a common height, we'll see what we're going to do when we do that, because we have one in the notes like that. All right, let's look at number 2. Let's look at number 2. It says, if the line x equals k divides the actual area of the region in example 1 into 2 regions of equal area, what is the value of k? Now, let's say that this was not on a calculator portion. Okay, so this one is non-calculator. So let's think about what this is saying. Okay, there's several different equations you could actually set up, but here's what makes sense to me. It says if the line x equals k divides the actual area into 2 regions of equal area. So let me kind of erase. I'm probably going to have to kind of draw this. I'll try to erase some of it, not all of it here. Okay. So I have some value of k between 1 and 4. that it splits it into equal area. So there's probably going to be, you know, somewhere, I don't know where it is exactly, but I mean, just, I don't know, I'm just kind of guessing. That probably looks a little flawed there. Does that look like equal area, this and this? No. So I couldn't do it way down here. So it's going to be somewhere, I don't know, in there that this area is the same as this area. Well, let's figure this out. Again, I'm doing this as if it's non-calculator. So first of all, let's figure out what the actual area even is. Are you able to figure out this exact value? Well, of course you are, because you could write that as x to the negative 2, and you could do the first fundamental and evaluate that. So that's going to be what? Increase the power by 1 and divide by new power. So if I increase the power by 1, that's x to the negative 1, negative, and I'm going to evaluate that from 1 to 4. Well, you know me, I like to pull the negative out. All those negatives confuse me. 1 over x from 1 to 4. So that would be the opposite of 1/4 minus 1. So that's going to end up being, of course, negative 3/4 here, but you have the negative. So the actual area under the curve is 3/4. So what are you saying? If k divides the actual area into equal things, wouldn't it be true that the integral from 1 to k of 1 over x squared dx, what would that have to be equal to? Well, that would have to be equal to 1/2 of this. Well, what is 1/2 of that? Well, 1/2 of that is 3/8. And so that is going to be your equation. Now let's get what that equation is. I'm doing something very similar here. I wanted to show that out because I wanted you to see that don't get confused by that k. Wouldn't it be true? I've already integrated, so let me just copy that down. The opposite of 1 over x, if I evaluate from 1 to k, and that needs to be 3/8. So let me keep going here. So I'd have the opposite of 1 over k minus 1, and it probably would make sense. Let me just, instead of having that negative there, are you with me that I could pop that to the other side, and that would be equal to 3/8, negative 3/8? I think we're good with that. So then what? Well, so here I go. If I bring that 1 over, I have 1 over k. If I add 1, think of that as being plus 8 over 8, 8 over 8, which is 5 over 8. And so if 1 over k is 5 over 8, then k is going to equal 8/5. So when k is 8/5, so I would have like 1.6. Obviously, I have to leave it in fraction form, but you could write it either way. That would split it into equal area. Very good, very good. All right, let's look at the next one. So you try this guy. Now look at what this is actually saying here. It says let f of x be, oh, goodness gravy. We're combining a few things. It says let f of x be that function defined as an integral. Use a trapezoidal sum with 4 equal subdivisions to approximate f of 1. Okay, what in the world is that even saying? So if f of x is this function, are you in agreement that f of 1 would be the integral from 0 to 1 of sine of t squared dt? Do you agree with that? Perfect. So in other words, what you're using the trapezoidal sum is, again, you need to approximate that. And look, I'm going to use my calculator, and you go, well, this is just stupid. I could just plug in the calculator and get the actual thing because the calculator will find that. Y'all, the point is, if they say an approximation, the actual answer is not the answer. You have to do an approximation, and you're going to have to show it out. So it doesn't matter that I'm using a calculator to get an approximation. You have to have it written out. So let's see. So basically, I'm saying use 4 equal subdivisions to approximate that integral. So let's go through our steps. Remember, our steps is the first thing we're going to do is actually find the height. We do that by the difference of the bounds over the number of trapezoids. So I get 1/4 or 0.25. I think I'm going to do this one in decimal. And so if I think about drawing it, now you go, I don't even know what that looks like. That's okay. Really, if I have between 0 and 1, I have 0.25, 0.5, 0.75, and I have 1. I could have my trapezoids. Here they come. I don't care what the function looks like. I have 1, 2, 3, 4 trapezoids. That's really all I need to do to draw. So f of 1, do these things have a common height? Yes, the common height is 1/4. So I'm going to bring out the 1/4. That's the common height. Again, if you want to do 1/4 or 0.25, sometimes I switch things. So I'll leave it as 0.25. That's the common height. Now I also have a common, the 1/2. So I can put it there. You know what? I'm going to move down here because I have a feeling I'm going to run out of space. So f of 1, I'm going to write 1/4 and 1/2. They don't take as long to write. Then I have my bases. Now I do like the first and last once in the inner ones twice. So remember what our function is. Our function is the sine of t squared. So when I'm plugging in these values, I am plugging into the sine of t squared. So the first one would be the sine of 0, because 0 squared is still 0. The last one would be the sine, and again, the sine of 1. So that's the first and the last. The middle ones, I would have 2 times what? The sine of 0.25 squared. Notice what I'm squaring. I'm not squaring the sine of 0.25. I'm just squaring that. So that squared goes there. I have the sine of 0.5 squared and the sine of 0.75 squared. Boom. Double parentheses there. And I want to get my answer. Now, as far as the calculator goes, look, if you want to, you can totally type it in just like I have here. A lot of times, people like to put their equation in. So what was our equation? First of all, let me make sure I'm in radian mode. Okay. So my equation was sine of x squared. Okay, wasn't that my equation? So really, okay, just want to be very clear. If I put that in my equation, I can type this whole thing. This would just be y1 of 0.25, y1 of 0.5, and y1 of 0.75. So you might like that typing better. Remember that I had a 1/8. I'm going to do the 1/4 times 1/2. I feel pretty confident in the fact that I can do that in my head. So on the outside, I have a 1/8, and then, oh, not there. And then what do I have? Well, again, I could type in y1 of 0. This one's just so easy that I'll just type in sine of 0. Again, I know that is actually 0, so some of you would say it's silly to even type that in, but we'll just go with it. So I have sine of 0 and sine of 1 plus 2 times, you do have to watch parentheses, the sine of y1. Okay, notice that closes that. I just hit, I'm stupid, not the sine of y1. I'm a ding dong. That would be y1 of, I just had it right, and I was kind of combining my two things. y1 of 0.25 plus y1 of 0.5, because remember, I put in my function sine of x squared. So it's squaring this x and then taking the sine, plus y1 of 0.75. Close that and then close that. So you've got to kind of watch your parentheses. So that, notice that I have this parentheses here, and I have that 2 parentheses. So you do have to watch parentheses in your typing, because I believe I need 3 at the end. That closes the y1, that closes the 2 times, and then that closes the multiplication. And I get the value. So I get f of 1 is approximately 0.316. Again, hopefully that didn't confuse you too much. If that y1 stuff confused you, then type it in like this. You could literally type it in exactly like it looks on the paper. Sometimes if the function is real complicated, this is just nice so that you don't have to, you know, type the function so many times. This one wasn't so bad, but it just gave you that thought. All right, last one. R of t in cars per minute gives the rate at which cars enter a parking garage from 0 to 10 minutes then. Using a trapezoidal sum with intervals deemed by the table. Very interesting. Estimate the number of cars that enter the garage in the first 10 minutes round to the nearest hole. Okay, such a great problem. So many things to point out. So first of all, you have to understand, okay, well, what am I doing? It doesn't tell you. I mean, I'm hoping if it says a trapezoidal sum, y'all, a Riemann sum and trapezoidal sums, what do? They approximate integrals. So I'm hoping that you go, okay, if what I'm really needing to do is I am trying to approximate this. That's what I'm trying to do. Because again, when I integrate cars per minute and I multiply by minutes, that integral will give me the cars. Well, estimate the number of cars. So that's what I'm supposed to be doing. It says a trapezoidal sum. Now let's draw this one because it's so important that you understand it says intervals deemed by the table, just like when we did Riemann. It doesn't have a common height. So let's draw, okay, this is what I'm trying to do. Let's draw. I have 0 and 2, 5, 7, and 10. And my function, a lot of the cars are coming in. I start at 0. Again, your drawing doesn't have to be like superbly accurate, but think about what you're going to do. You have to find the area. This is a trapezoidal sum. So you are finding the area of each of those trapezoids. Put a big fat star. Not equal heights. So friend, when it's not equal heights, You cannot pull out a common height because there isn't one. So this integral sorry, it's 10, not 12, is going to be what? Well, look, let's write down the trapezoidal, the area of a trapezoid. Okay, it is 1/2 base 1 plus base 2 times h. Now, do they all have a 1/2? Yes. So I like to pull out the 1/2. You can always pull out a 1/2. But when I go to trapezoid 1, 2, 3, and 4, y'all, you can't pull out anything in there because it's not common. So for each trapezoid, I'm going to have the height. Now, where is the height? Remember, the height is going to be this. Now, I realized this first when you're like, Ms. Pruitt, that's a triangle, so can I just do a triangle? Yes, but I do trapezoids and I don't do them separately. I do them all the same. So I just kind of get in system. So yes, that is a triangle and you can do that. But the heights, so this height would be 2, this height would be 3, that height would be 2, and that height would be 3. So again, for you to understand, the heights would be the difference of these things, right? So let's look at my picture. This first trapezoid, I'm going to do a height of 2. Height of 2, I just put my height first. My base 1 and base 2 are going to be the y values of these two things. Now again, I feel pretty good that I can add those together in my head and put that. The next trapezoid would be a height of 3, and I would add base 2, this base, and this base. So I'd be looking at 5.5 and 8. Now, you can do one of two things. Some of you, especially if you have to type it in, you're like, I feel pretty good that I can add that and put 13.5. If you don't want to add that and you want the calculator to do it, then write it that way. Whatever, I'm going to write it out just so you're seeing where I'm getting these numbers. The next trapezoid, trapezoid 3, would have a height of 2. The two bases would be 8 plus 11. And the last trapezoid has a height of 3, and it would have a base of 11 and 12. And so that would be your equation. If I wanted to type this in, again, I could type it in exactly like it looks there for the speed of typing. I have 0.5 times 2 times 5.5 plus, I'm going to go ahead and do the addition in my head because I feel like I can. Okay, so I do 3 times 13.5 plus 2 times, that would be 19, plus 3 times 23. So again, I just did the adding in my head, but if you don't want to do that, that's fine. And I would get 79.25. It said round to the nearest car, so that would be 79 cars. All right, peace out.